Math 1332, Chapter 2, Set Theory, Section 3, Using Venn Diagrams to Study Set Operations. Video 1, 2 and 3 set Venn diagrams. In this section, we're going to explore how we can use Venn diagrams to answer some questions about set operations. In particular, to answer the question, are two set operations equal? Because sometimes it looks like just a mess of algebra, but you can boil it down to some pretty simple set operations. We're going to start by looking at a generic two-set Venn diagram. Now, we've already looked at these in previous videos. Just a reminder, in a Venn diagram, you have a rectangle that represents your universal set, even if the universal set isn't explicitly defined. And for each set inside the universe that we're discussing, we have a circle to represent it. We did talk about some specific instances with two-circle Venn diagrams. For example, in general, when you have a two-circle Venn diagram, you have two intersecting circles, where the region in the center, if I could just fill that in for a second, the region in the center would represent their intersection. Let me try something real quick. There we go. Make that a little bit thinner. 1 second, folks. There we go. So since we don't know whether or not two sets have an intersection, we just assume that they do. And when we draw the Venn diagram, we make sure that the circles overlap. Now, in the event that they didn't have an intersection, that they were disjoint sets, then we could just argue that that football in the middle is empty. Or if we knew in advance that two sets were disjoint, we could draw their circles so that they don't overlap. And that would be a good visual representation to show two disjoint sets. But in general, when you have two sets in a universe, if you don't know anything more specific about them, you can't just assume that their intersection is empty. And so you have to represent a possible intersection by overlapping the two circles. Just as a side note, there was one other thing that we could show about two sets related to each other in a Venn diagram, and that's if we had subsets. For example, if we had A was a subset of B, or even A is a proper subset of B, meaning that A is inside of B but is not equal to B, then there was a way to illustrate that in a Venn diagram by, 1 second, let's make this a circle, by literally making sure that one of the circles is inside of the other. So this would be a visual representation of A being a subset of B. If we wanted B to be a subset of A, we would have to do the opposite, and we would have to make set B small enough and positioned correctly so that it would be contained inside of circle A. And I use the word circle loosely here in a topological sense, which is a really nerdy joke, but we won't worry about that. But in general, when you are drawing a Venn diagram for two sets, you just draw two circles that overlap. And for reference purposes, we want to be able to refer to the regions that these overlapping circles partition the universe into. And what do I mean by that? I mean that there are 4 regions. I'll just point them out real quick. One of them is right here, right here, right here, and right there. But for reference purposes, we need to give them more definitive names. Additionally, I want to take this A and this B and move them outside of the circles for a second so that they don't get in the way as I label these regions. All right, so what do we call these regions? Well, they have really creative names. The first region that is in A but not in B is called region 1, and we'll use Roman numerals to represent them. The intersection is called region 2. Not sure where the 2 went. Let's try that again. There we go. The region that belongs to circle B but not circle A, or rather set B but not set A, is region 3. And the region outside of both circles but in the rest of the universe is going to be called region 4. So from this point forward, anytime we draw a Venn diagram and want to refer to regions, we will refer to them as such. In fact, we should go ahead and enumerate this here. Region 1 will always be inside A, outside B. Okay. I get the feeling I'm going to need to widen this text box a little. Region 2 is always going to be inside A and inside B. Region 3 is always going to be outside A and inside B. And region 4 is always going to be outside A and outside B. Now, just as a side note, you could also define these regions specifically in terms of intersections and complements. Now, what do I mean by that? Well, to belong to two regions means that you belong to, to belong to two sets means that you belong to their intersection. For example, region 2, we'll highlight that real quick. Region 2 is both inside A and inside of B, so it stands to reason that region 2 represents A intersect B. So we could easily draw that. And we could draw something like this. Region 2, let's put that right here, is A intersect B. But what would region 1 be? Now, if you're paying close attention to the previous videos, you might go, that's just A minus B, because we start with circle A and then remove the part that overlaps with B. But if we think of it in terms of intersection, being inside of A means A and intersection. Being outside of B means B complement. So we could just as easily say that region 1 is represented by A intersect B complement. And if we did the same thing for region 3, well, it is outside of A, although that's outside is spelled incorrectly, so it belongs to A complement. And it's inside of B, which means it's inside of B, and therefore region 3 is represented by A complement intersect B. That outside is going to bother me. Y'all should know by now I'm a little bit OCD about these things. Might as well fix that too. Ah, there goes the line break I didn't want. There we go. All right, so anyway, so what's region 4? Well, region 4 is outside of A and outside of B, which means region 4 belongs to the complement of A, and I'm sorry, I'm using C for complement, not apostrophes, and the complement of B. Let me fix all these complements. And I should have warned you when I did the video about complements that there is more than one notation for complement. I know of at least 4 notations for the complement of a set. Let's see, that goes there and that goes here. And sometimes if I'm not careful, I'll accidentally write a different version for it. For example, this, which with what looks like an exponent of C, is a standard notation for complement, as is that, A with a bar over it. But I'll try to be consistent and use the apostrophe notation for complement. So what do I want you to know from this picture? Well, what I really want you to know from this picture is really just the picture. So as long as you can know this, where regions 1, 2, 3, and 4 are located, you're okay. Just remember they go from left to right through the middle, starting here, 1, 2, 3, and then 4 is just outside somewhere. So what about a 3-set Venn diagram? Well, a 3-set Venn diagram, as you can imagine, is going to require 3 circles. Because if we have 3 sets, then each one is represented by a circle. Now, because a 3-set Venn diagram typically has 3 circles in it, we're going to want a larger rectangle to hold all those circles. In fact, you could even argue that a square would be sufficient, but we'll just do a rectangle. And of course, that rectangle will represent our universe. And if we have 3 sets, generically, we could call them A, B, and C. So let me just start with 3 circles. And I better make them fairly large. I realize that's not quite where I want it right now. Let's select this circle and move it over and make it a little bit larger. All right, so we got these 3 circles, which we'll call A, B, and C in a moment. And in general, we don't know if any of them have anything in common with each other. For example, if the first and second circles, which represent sets, have any elements in common, or if the first and third circle or the second and third circle. Because of that, we need to make sure we have every possible intersection. One way to think about a 3-set Venn diagram is to think about a 2-set Venn diagram first. And remember, this 3-set Venn diagram, this 2-set Venn diagram, has 4 regions. I'm not going to label them 1, 2, 3, and 4 right now because we're about to bring in the next circle, but the 4 regions are here. And when we bring in a 3rd set, it needs to overlap all of the 4 pre-existing regions. So let's take this 3rd circle and figure out where to put it. It must overlap regions 1, 2, 3, and 4 in this diagram. And so if we put it up here somewhere, it could be as low as there, but I like to have some space to write everything in. There are currently 4 regions. This circle is going to cut each one of them, so which means we're going to have 8 regions now. And that's what a 3-circle Venn diagram looks like. For reference purposes, we'll call these sets A, B, and C. I know that's a really lame thing to call them. We'll put C down here since B was up here in the previous Venn diagram. Doesn't really matter. But now we have 8 regions. And just like before, we need to be able to, well, first, let me move all this over because I'm going to need room to the right of it. Everybody move. Looks like I missed the B and the C. That's okay. I'll fix that in a second. And I really don't like where that A is. I know it's persnickety, but it was bothering me. All right, so we have 8 regions in a 3-set Venn diagram, and we're going to number them the same way we did before using Roman numerals. But since we have 8 regions, we need to decide where to start numbering them. Well, we're going to number them starting the same way that we started into the 2-circle Venn diagram. We're going to start with the part that only belongs to A and move from left to right. So if we start right here and put a Roman numeral 1, and then move left to right with a Roman numeral 2, and then Roman numeral 3. And then you'll notice we've got this strip of 3 regions going right across here. So we're going to continue numbering across those. We're kind of numbering these left to right, top to bottom, like we're writing a paragraph. All right, so we'll go to this region next and call it region 4. Forgot I had caps lock on. Then the next region we'll call region 5, right here. And the next region we'll call region 6. Now, if you're not familiar with Roman numerals, IV is 4 and VI is 6. The reason is pretty straightforward. You may not know a lot about Roman numerals, but you're about to learn a little something. This is the Roman numeral for 1. Roman numeral for 5 is V, and the reason is if you hold up your hand, you see a V shape right here. And when you have a smaller number in front of a larger number, like IV, this is a 1 before a 5, so this literally means 1 before 5, which is 4. But if you have a smaller number after a larger number, this is 1 after 5, and the number 1 after 5 is 6. So if you're wondering what was up with Roman numerals, that's a very short crash course on them. So anyway, the 3 regions across the middle are labeled 4, 5, and 6. And then the region that belongs to circle C only is going to be region 7, which is VII. And where's the 8th region? Oh, outside in the rest of the universe. So region 8 is out here, VIII. It's not a catastrophe if you use regular numbers, Arabic numerals, to label them 1, 2, 3, 4, 5, 6, 7, 8 instead of Roman numerals. But in some of our problems, the elements of these sets will be numbers. And so we can't use numbers to label the regions because then we'll get confused between what is a name of a region and what is an actual element in the set. Excuse me. I'd like to do one other thing before we wrap up this video. I would like to try to describe all 8 of these regions the same way that we did back here. Not necessarily in terms of inside and outside of, although we'll say that verbally, I'm not going to write it, but I would like to try to describe each region. Excuse me. I'd like to try to describe each region in terms of the intersection of a circle and the complement of a circle. Just remember that saying that you're in the intersection of a circle means that you are inside the circle, but saying that you are in the intersection of the circle's complement, meaning that you are outside of the circle. So just as a reminder, like this first one, region 1, A intersect B complement. A means inside of A, B complement means outside of B, and the region that is inside of A but outside of B is region 1. So I want to attempt to just quickly describe all 8 of these regions in terms of circles and their complements and intersections. And it's not nearly as hard as it seems. All you have to do for each region is ask yourself, for each circle, is it inside or outside? For example, for region 1 is inside of A and outside of B and outside of C. So I'll say that again. Inside of A, and, intersection is and, outside of B, so B complement, and outside of C, so C complement. Let's try region 2, and then I'm going to invite you to pause the video and see if you can come up with the other 6. All right, region 2 is right here. It is inside circle A, it is inside circle B, but it is outside of circle C. So let's say that again, and this time write some things. Inside of A, so we write the A, and, so we write the intersection. Inside of B, so we write the B, and outside of C, so it intersects C complement. All right, I invite you to pause the video. I'm going to go ahead and set them up. But I invite you to pause the video and see if you can come up with these set operations that describe the remaining 6 regions, 3, 4, 5, 6, 7, and 8. And remember, for each one, you're basically going to do a triple intersection, the intersection of 3 sets. And whether or not you use a set or its complement depends upon whether or not the region is inside or outside of that set. All right, so go ahead and pause the video and see if you can come up with the rest of these. All right, hopefully you took a chance to pause the video and try them. I'm going to go through them fairly quickly. All right, region 3 is inside circle B, but outside everything else. So it's outside of A, and inside of B, and outside of C. Region 4 is inside of A and C, but outside of B. So it's outside of B, but inside of everything else. Inside of A, and outside of B, and inside of C. Region 5 is in all 3 circles. It's what I call the triple intersection of the Venn diagram because it's where all 3 circles overlap. So it is A intersect B intersect C. Region 6 is in circle B and circle C, but not circle A. So it is outside of A, and inside of B, and inside of C. Region 7 is in circle C only, so it is outside of A and outside of B. So outside of A, and outside of B, and inside of C, excuse me. Pardon me. Region 8 is outside of all the circles. So region 8 represents A complement, intersect B complement, intersect C complement. So it's not too difficult to identify each region individually in terms of intersections of circles and their complements. You simply have to ask yourself which circle is a region inside, which circle is a region outside, and then take the intersection accordingly.